Um, so welcome everyone to this special webinar by Gonit Sora. We have today Professor Sujatha Ramdorai with us. And she's going to speak about Ramanujan's tau function and modular forms. So before she speaks, let me introduce very briefly Professor Sujatha. Professor Sujatha is now a professor in the University of British Columbia in Vancouver, Canada, where she holds a Canada Research Chair. She was previously a professor in the Tata Institute of Fundamental Research, Mumbai, and then she moved to Canada. So she has won several awards. Let me just mention three of them. She won the prestigious Santi Swarup Bhatnagar Award in 2004. Then she won the ICTP Ramanujan Prize in 2006. She was the first Indian and the only female to win this award. And very recently in 2020, she won the Krieger-Nelson Prize for her exceptional contributions to mathematics research. She has been a very powerful supporter of Gonit Sora for many years now, and I'm very pleased and honored that Professor Sujatha has agreed to give this talk. So, Madam, please, you can go ahead.
Thank you, Manjil. I've known Manjil for many years now. In fact, I remember how many years now, Manjil? I mean, before he started his graduate studies, and I was so happy when he started this Gonit Sora. And because that's one of my dreams as well, to make mathematics more inclusive and for people to understand how useful mathematics is. So it's very nice to see Manjil both evolve as a mathematician and simultaneously to see that Gonit Sora has been sustained so well and is doing so well. So thanks for the kind words, Manjil.
Thank you.
And Manjil told me that there were a few others who had spoken about modular forms and elliptic curves. So I thought I'll speak about one aspect of modular forms, which is related to India's great mathematician Ramanujan. And this year, by the way, 2020, it's 100 years since Ramanujan passed away. And so we'll talk about his tau function. So let me start with introducing the notation for the numbers which I'll be using. I don't think I'll use many of them, but let me introduce the numbers anyway. Z, these are the set of integers. So these are the consisting of both negative integers as well as positive, 0 included. So it goes from minus infinity to plus infinity. And then these are the numbers -5, -4, -3, so on, all the way up to 0, 1, 2, 3, and so on. And next is the set of natural numbers, which I'll denote by n. It's also the same as the positive integers. So n is also z plus. And then we have the set of real numbers. This is just the real number line from minus infinity to infinity, consisting of all rational numbers, irrational numbers, all of them. And then finally, the set of complex numbers. And for those of you who know a little more about abstract mathematics, the last two are what are called fields. Real numbers and complex numbers are fields. The first one, the integers, is just a ring. And we are going to talk about what are called multiplicative functions. So multiplicative functions, first one learns about a special class of functions called arithmetic functions, and you learn about them in an elementary number theory course. So let's define arithmetic functions. These are just functions from z plus into complex numbers. So these are just functions from the positive integers into the complex numbers. No demands, they are just functions. And then we say that an arithmetic function is multiplicative if it respects multiplication. So f is an arithmetic function. So it's a function from positive integers with values in the complex numbers. And if f satisfies the property that when I take two numbers which are co-prime, that is m and n have no common divisors, and then f of mn becomes equal to f of m times f of n. So whether you take the value of the function after multiplication or before multiplication on two numbers which are co-prime, which do not have any common divisors, then it's called a multiplicative function. So let's see some examples. Okay, before that, there's another stronger concept. This is totally multiplicative, where totally multiplicative functions are multiplicative functions where this necessity of the two numbers being co-prime is removed. So f of mn should be equal to f of m times f of n for any pair of integers m and n which are in z plus. So these are the three gradations. So you start with arithmetic functions. Inside arithmetic functions, you have the multiplicative functions, and then you have inside multiplicative functions, you have the totally multiplicative functions. Here are some examples. So the first one is what's called the sigma function. Sigma of n, this is also called the sum of divisors function. So what you do is you take a positive integer n, then look at all the divisors of n. So this notation means k dividing n. So take all the divisors of n and then add those divisors. So that is called the sum of divisors function. So for instance, let's look at sigma of 2. So the divisors of 2 is the smallest prime number. So 1 and 2 are the only divisors. So you add them up, that's 3. Sigma of 12, the divisors of 12 are 1, 2, 3, 4, 6, and 12. So you add them up, you get 28. So that's how the sigma function is defined. Then there's another function called the tau function. This only counts the number of divisors of n. So for instance, if you take tau of 2, because 2 is again, as I mentioned, it's the smallest prime. So 1 and 2 are the only divisors of 2. So tau of 2 is 2. And then tau of 12, take all the divisors of 12 and they are here 1, 2, 3, 4, 6, and 12. So there are 6 of them. So their tau of 12 is 6. Now the other function which we have all seen is the Euler phi function. The Euler phi function is the number of integers which are less than or equal to n and which are relatively prime to n. So which means that you collect all the integers which are less than n and such that n and these integers do not have any common divisor. So for instance, if you take 2, because 2 is a prime number again, phi of 2 is only 1 because the only divisor of 2 which is relatively prime to 2 is 1. So therefore phi of 2 is 1. And for 12, we need to collect all the divisors of 12 which do not have a common divisor with 12. So 2 is out because 2 and 12 have a common divisor, namely 2 itself. 3 is out. 4 is out. 6 is out, 12 is out. So all these divisors are out. So you look at all the other integers which are less than 12, then they don't have a common divisor with 12. So you can check that phi of 12 is 5. Okay. So now here is a simple observation. Take a prime number. Then of course the Euler phi function on p is p minus 1. Phi of p is p minus 1 because by definition a prime number, all the numbers smaller than that prime do not divide the prime. So phi of p has p minus 1 is equal to p minus 1. All the numbers which are less than p are integers which are relatively prime to p. So phi of p is p minus 1. And sigma, the sum of divisors, this function on p, sigma of p is always equal to phi of p plus tau of p. Tau of p is the number of divisors. So number of divisors from the plus the Euler phi function is sigma of p. So this is something you can check. In fact, it's not difficult to prove. So let's do this. Let's verify this. For instance, let's do it for p equals 7. Then phi of p is p minus 1, which is 6. And tau of p you can check is 2. And then sigma of p is 8. So then you check the 2 plus 6 is equal to 8. Okay. So these are some of the simple identities between some of the known multiplicative functions. Now I'm going to change tack slightly and I'm going to introduce a completely different kind of function. And this is in fact a totally different kind of phenomenon. So I'm going to introduce the Riemann zeta function. So the Riemann zeta function is a function of a complex variable. So this S here, so this is a zeta, Riemann zeta. Riemann was a great German mathematician. He studied this function. So S is a complex variable. So zeta of S is defined to be summation of 1 over n to the power S, whereas n varies from 1 to infinity. So you take all the natural numbers, raise them to the power S, take their reciprocal and add them. And remember, Riemann was doing this. You'll see, he was doing this at a time when it wasn't even clear what this infinite sum means. What does it mean? Today we know we can talk about convergence and so on. But when he did it, it wasn't even clear if this had a meaning, but he still gave this a meaning, and he proved some remarkable properties for this Riemann zeta function. And you should know that there are still a lot of open questions about the Riemann zeta function. And in fact, there's a $1 million problem. The Millennium Problems, one of the Millennium Problems, asks for what values of S is zeta of S equal to 0. Okay, so well, it asks for values of the zeta function. And in fact, what we do know is zeta of S, in fact, there are a lot of unknowns about the Riemann zeta function. You don't even know for what values of integers, what kind of values does it take. So this is a completely, and I think tens of thousands of papers have been written on the Riemann zeta function. And there are very precise conjectures on the behavior of the Riemann zeta function. But what I would like to focus on today is this identity by Euler, who was another great mathematician, Swiss mathematician. He expressed this infinite sum here, 1 plus 1 over 2 to the power s plus 1 over 3 to the power s plus so on. He expressed this as an infinite product. And the product is expressed in terms of primes. So take this infinite product, 1 upon 1 minus 1 over p to the power s. That's what this p to the power minus s means. So that's 1 over p to the power s. So take this infinite product. So that is zeta of s. So you have converted an infinite sum into an infinite product. And again, mysteriously, there are lots of functions in mathematics which have this property that you can express that function both as an infinite sum as well as an infinite product. So here's a picture of Riemann. So he's a German mathematician from the 19th century. And by his time, there was some vague notion of what it means for an infinite product to make sense or an infinite sum to make sense. But it wasn't still as precise as we know it today in abstract mathematics. And here is Euler. So Euler was even before Riemann. And again, Euler studied these infinite sums at a time when convergence was very vague. Nobody knew what it meant for an infinite sum to have a value precisely. Now, but remarkably, this Euler's identity converts this infinite sum into an infinite product at a time when nobody knew what these things meant precisely. And in 1916, Ramanujan introduced a function which is now called Ramanujan's tau function. And I'm going to define the function. I'm going to write that function for you. It'll appear mysterious, and that's again one of the examples of Ramanujan's genius. Even though he wasn't formally schooled, he had great intuition. He never had a proper teacher. He was completely self-taught. But intuitively, he understood what it must mean for an infinite product to make sense or for an infinite sum to make sense and so on. And this is Ramanujan's tau function. So to define it, first consider this quantity. Let me just call it delta. That's what it is called. So that is this crazy looking infinite product. I'll explain each of the sums, each of the terms here. So Q is e to the power 2 pi I z. So which means Q is like, we all know Euler's formula for e to the power 2 pi I z, right? So this is cos 2 pi I theta plus sine I sine theta. E to the power I theta is cos theta plus I sine theta. So Q is e to the power 2 pi I z, where z is a complex number which is in the upper half plane. So think of the complex plane as the x-axis and the y-axis. And then when you express a complex number in terms of Cartesian pairs, you can think of it as x plus iy, or a pair xy, where x and y are real numbers. So by the upper half plane, we just mean that we just consider the part of the plane which is above the x-axis. So in other words, it looks like x plus iy, where x is, okay, let me even take the special case that x is equal to 0, y is greater than 0. This is the upper half plane, and so this is the imaginary axis. But the upper half plane, by the upper half plane, I mean everything that lies above the x-axis. And in the upper half plane, you can take z, and then you look at e to the power 2 pi I z, and then this is q is usually short form for e to the power 2 pi I z. And then you take this crazy looking infinite product, q times 1 minus q to the power n, 2 to the power 4. So this is really, you should write this as delta of z, where z is in the upper half plane. So it's a function on the upper half plane, and it has this expression as an infinite product. But then, strangely enough, it also has an expression as an infinite sum, where you can express it as summation q to the power n times some coefficients, and those coefficients are called tau of n. So it's a very convoluted way of defining it. And it's really remarkable that Ramanujan understood that this infinite product has an expression as an infinite sum. And he himself computed the first n values of, so here is a picture of Ramanujan. And you see, I mean, again, he was, later, of course, much later than Riemann and Euler. I don't know if he knew of Riemann's work or Euler's work. Or at least that they did what they did fully and so on. But it's really, I find it really remarkable, and often think what it would have meant for all of them to be together in one place and to discuss what they discovered or what they knew. Okay, so again, I'm stressing this. Delta has an expression both as an infinite product and an infinite sum. And Ramanujan himself calculated the first 30 values for tau of n, that is n from 1 to 30. So tau of 1 is 1, tau of 2 is minus 24, tau of 3 is 252, and so on. And look, the numbers get larger and larger, and they change signs. So they're both positive and negative. And how did he do this? Of course, today we understand, people understand how he must have done it. And that's because this tau function has connections to the Euler phi function. And Ramanujan must have known it. And that's one way of computing these values of tau. But more remarkably, Ramanujan suspected that this tau function is multiplicative. That is, if you take two integers m and n, which are co-prime, then tau of mn is equal to tau of m times tau of n. Remember, that's how we defined a multiplicative function. And Ramanujan suspected that this tau function must be multiplicative. And this property of multiplicativity was proved by Model in 1970, shortly after Ramanujan came across, defined this tau function. And there are more conjectures related to the tau function. Let me mention a few of those. So apart from the multiplicativity property here, it's multiplicativity here, he also observed the following properties. So the first is how it behaves on powers of prime. Remember, we said tau is multiplicative, means tau of m times n is equal to tau of m times tau of n, but under the condition that m and n are relatively prime. Whereas a number like this, p to the power r plus 1, of course, I can write it as p times p to the power r. But they are not relatively prime. They are both divisible by p. So what happens to tau? How does tau behave on powers of primes? And why are we interested in this? Because if we know that we are working with a multiplicative function, then it is enough to know how tau behaves on prime powers. Because then by the fundamental theorem of arithmetic, if I'm given any positive integer, I can break that positive integer as a product of primes. And if I know the value of tau on powers of prime numbers, then I know the value of tau on any integer, on any positive integer. And Ramanujan conjectured that tau of p to the power r plus 1 should behave like this. It's if not for the second term, it is multiplicative. So tau of p times tau of p to the power r, but then there is this error term, p to the power 11 times tau of p to the power r minus 1. So he also observed the following properties. He proved this for small primes and conjectured that this should be true in general. And then the other remarkable thing that he conjectured was that the absolute value of the tau on a prime should be less than or equal to 2 square root of p to the power 11. And this should be true for all primes p. So this is Ramanujan's conjecture on the tau function, and results related to this find use, and they're part of a whole grand scheme in number theory. And things related to the values of tau function find applications constantly in very powerful theorems. As recently as in 2010 or even later, there was a big theorem called the Sato-Tate conjecture, which was proved, which in turn used lots of properties of the tau function. And this first conjecture on the behavior of tau on powers of prime numbers was again proved by Model. The second one was only proved in 1976 by Deligne, for which he was awarded the Fields Medal. So you can see the power of Ramanujan's insights. So 1916, it took 60 years and all the tools of modern mathematics to prove this conjecture, which he intuitively somehow saw. And like I said, Deligne was given awarded the Fields Medal for this. Okay, here's a picture of Louis Model. And here's another picture of Pierre Deligne. By the way, Deligne was one of the youngest people to win the Fields Medal and to do really great mathematics at a very young age. And he always, I mean, when Deligne first visited TIFR, I think he was asked, when in his talk, he said that he owes all his honors in mathematics to Ramanujan, because he worked on so much of mathematics that he worked on was related to mathematics that came from Ramanujan's work. Now recall again, let's go back to the sum of divisors function. We had the sum of divisors function sigma of n, which just added up all the divisors of n. So that was the sum of divisors. You can tweak that to define sigma kn for any integer k. And that's defined by just taking all the divisors d dividing n and raising that to this power k. So you can do it both for positive or negative integers. So sigma k of n, you can just say is summation of d to the power k, where d divides n. So when k is 1, you get the usual sigma of n. And here are some facts about tau. And all of this, again, Ramanujan knew. So tau of n had one of these, tau of n has this property, sigma of 11, where sigma 11 is this sigma k, and so on. So just look at this complicated formula. And Ramanujan already knew it for some of the small n. I told you that he had computed the values of tau for the small n's, and he saw this pattern for some of them. And so this 691, again, that's a very interesting prime number related to the tau function, which has later led to very deep mathematics in number theory, the 691, and which comes up again in the connection between modular forms and elliptic curves. 691 was the first prime to provide a clue to people like Deligne and Serre that there is some connection between modular forms and elliptic curves. Okay, so now let's come to modular forms. I'll make this statement and then I'll explain everything in this statement. So this delta, remember delta was the function, defining function for Ramanujan's tau function. So let's go back. I'll show you what delta was. Delta was this infinite product and infinite sum. Yeah. Yeah, so delta was this infinite product, which was also the infinite sum tau of n q to the power n. Okay, so it is a modular form. So what does it mean for something to be a modular form? So remember I mentioned that you should really think of delta as a function on the upper half plane. So it's a function of the complex variable, where the complex variable is in the upper half plane. So let's define a modular forms, but I'll start by saying that delta is a modular form of weight 12 for SL2Z. So think of this as a mantra. It's a modular form of weight 12 for SL2Z. Now what is SL2Z? SL2Z is a set of all 2 by 2 matrices with integer entries and determinant equal to 1. So in other words, it just consists of matrices A, B, C, D, where A, B, C, D are integers, and the determinant is AD minus BC. That should be equal to 1. So this is a group, and here are some examples of elements which are in SL2Z. Obviously, all of these have the property that the determinant is 1. 1 minus 0, 1 minus 0, 0 minus of minus 1, so the determinant is 1. So these are all examples of elements in SL2Z. Now, this SL2Z acts on the upper half plane. So that's how the connection comes to a modular form. SL2Z acts on the upper half plane. And a modular form of weight k, where k is an integer greater than or equal to 1 with respect to SL2Z, is nothing but a holomorphic function on the upper half plane, H, satisfying complex valued holomorphic function, which satisfies this property. So I can take Z, which is a point in the upper half plane, and then think of A, B, C, D. This is an element in SL2Z. So when it acts on a point Z in the upper half plane, you're again in the upper half plane. AZ plus B over CZ plus D is again in the upper half plane. And F on this transformed point, after you transform this point Z by an element in SL2Z, it is related to the original value F of Z by just CZ plus D raised to the power K. So that's the role of K here. That's the weight. That's how the weight comes in. And then this is the transforming property. So this tells us how this function, this holomorphic function, behaves when I take a point in the upper half plane and operate that point by an element in SL2Z. And then the other important property is that it has to be holomorphic as I go towards the infinity on the y-axis. So on the upper half plane, you have this special point, right? You look at the y-axis and it's going to infinity. So as I tend to that point, infinity in the y-axis, then F continues to be holomorphic. It doesn't acquire a pole. So once you know this, then pure complex analysis will tell you that any such modular form has to be of the form F is equal to summation AI q to the power I, where AI's are complex numbers and Q is again e to the power 2 pi IZ q to the power I. So you can forget all that I said about modular forms and think of a modular form as an infinite sum. And you call that as a Q expansion. So it is just a modular form is a function on the upper half plane, and you forget all the transforming properties. You just remember that F can be written as summation AN QN, where AN are complex numbers. N goes from 0 to infinity, and Q is e to the power 2 pi IZ, where Z is in the upper half plane. So now that's what I've written here. So every modular form, and this is called the Q series expansion or the Fourier expansion. And it looks like AN q to the power n, where AIs are complex numbers, and Q is again e to the power 2 pi IZ, where Z is in the upper half plane. So now associated to a modular form, you can define what's called an L function, L of Fs, where S is a complex variable, where you just collect these coefficients AN and then look at AN upon n to the power S. So this looks remarkably like the Riemann zeta function. If I just take all the ANs to be 1, we get back the Riemann zeta function. Right? So these L functions are glorious avatars of Riemann zeta function in a different context. And again, like the Riemann zeta function, which had the property of being able to express it as an infinite sum as well as an infinite product, these L functions have the same property. You can also write them as an infinite product. And so for instance, if we do that with this special modular form, Ramanujan's tau function modular form delta, then you can write L of delta S is tau of n upon n of S. And you can also exhibit it as an infinite product over primes, 1 minus tau of p to the power s, plus 1 over p to the power s minus 11, the whole thing raised to negative inverse. So this again, we saw it with for the Riemann zeta function. You could express it as an infinite product as well as an infinite sum. Okay, of course, I don't think Ramanujan did all this, though he might have had some inkling. But at that time, modular forms were probably not fully developed. And it's interesting to see how much of an intuition he had and how much Ramanujan saw these modular forms in his own way. So I've almost come to the end of my talk. I just want to close by saying this L function, of course, you can ask, what does it mean? This is an infinite product. What does it mean? So here we have to talk about where it acquires a meaning, because this is a holomorphic function. And then a holomorphic function, you have to know where it converges, right? So there are very precise conjectures on which part of the plane this function converges and so on. So there are very precise conjectures. Some of them are open, some of them are proved. But again, like the Riemann zeta function, there are a whole range of questions and conjectures related to the L function. And in fact, an abstract question you can ask is, what are the functions, complex valued functions or functions of a complex variable, which have this expression both as an infinite sum as well as an infinite product? Can we describe them? Is there some way of identifying them? After all, there are so many examples. We have these L functions and modular forms. By the way, there are plenty and modular forms. Modular forms have been very well understood. So you understand that there are lots of functions. All the L functions of modular forms have this property. But an abstract question would be, what are the functions which have this property? Functions of a complex variable which have this property. That is still a subject of research and very active area of research, important one, both from the complex analysis point of view as well as number theory point of view. Okay, so let me close this by saying that Ramanujan's conjectures, we saw those conjectures of Ramanujan, which he started by working with this tau function. You know, the multiplicativity of the tau function, the behavior of the tau function on powers of prime numbers, and also the tau function on primes. What are the values of the tau functions on primes? And these conjectures have led to a whole variety of techniques and ideas in number theory, in arithmetic in the last century for 100 years. And to just give you an example, here are some, I'm just going to make some statements. Langland's program, Weil conjectures. Now, by the way, Deligne got the Fields Medal for proving these Weil conjectures. And then Sato-Tate conjectures. All of these, much of these mathematics somehow in one form or the other were inspired or have connections to Ramanujan's work, especially his modular form. And Ramanujan's work finds applications in diverse areas: computer science, electrical engineering, signal processing problems, graph theory, string theory, black holes. For instance, this is in theoretical physics. It's very bizarre, but I told you there are lots of things which are completely mysterious about the Riemann zeta function, in particular the values of the Riemann zeta function. Now, in string theory or in the study of black holes, you strangely come across these numbers. And people have been able to make a connection between those numbers and expected values of the Riemann zeta function. And this is, again, it's really bizarre. I mean, why should there be this connection between cosmology or string theory and then something that's purely mathematical, Riemann zeta function, which itself we do not understand much about? So again, last year, like I said, there was this, this year is 100 years since Ramanujan's death. And last year, 2018 or 2019, the Royal Society held a special conference to honor Ramanujan for his death anniversary. And they put up a very beautiful program. You can Google Royal Society Ramanujan and you'll find it on the Google. You can listen to all the lectures where people spoke about Ramanujan's work. And people from all these different areas came and spoke about, you know, it was computer science, but then they would say how Ramanujan's work finds application in computer science and so on. So it's very fascinating. And if people are interested, you can go and listen to that. It's available on the Royal Society website. And more than half a dozen, you know, in mathematics, there are these top prizes, the Fields Medal and the Abel Prize. And more than half a dozen, in fact, I would say close to 10 prizes, combining Fields Medal and Abel prizes, have been inspired by Ramanujan's work. People who got the Fields Medal or Abel Prize, their work was heavily influenced or had connections to Ramanujan's work. So you can see from this what a lasting, indelible effect Ramanujan's insights and Ramanujan's mathematics has had and will continue to have in the years to come. And let me close this by this special quote of Rademacher, who was a German mathematician and who saw this strength in Ramanujan a long time back. So you see, he was in 1892 to 1960s. And he says, he was a number theorist, but he did various other things. He was also an analyst and so on. So in one of his works, he says, after discovering something, he says, this is again an instance of Ramanujan's gift of divination. Not only that he foresaw or unveiled hitherto unknown fields, but most of his conjectures lead back to sources of great depth and abundant yield. And we are continuing to witness that to this day, and we'll continue to witness this, I feel, for many years in the future. So thank you very much, and I'll be happy to take any questions that you might have.
Thank you so much for the very nice talk. So I have several questions from the participants already.
Okay, I might, okay, disclaimer, I might not know all the answers. But I'll try. Yeah, go ahead.
Yeah. So let me just. So this was one of the first questions. So why does the codomain of arithmetic functions chosen as the set of complex numbers?
No, because most of the functions, like we saw already, this tau of n takes values in complex numbers. And also the complex numbers, in some sense, if it can, you can allow it to take values integer valued or real valued or whatever. But you know that there are lots of multiplicative functions which take values in the complex numbers. And even if it takes values in the integers or real numbers, we know that all of these are sitting inside the complex numbers. So you don't lose anything by taking the largest codomain.
Okay. So there is a question which asks, is there a closed form formula for Ramanujan's tau function?
Closed form, yes, there is, which is related to the phi function. I don't remember it offhand, but I mean, there are lots of articles, but this tau function, people study it from different points of view. Our analytic number theorists will study it, complex analysis people will study it, and then hardcore arithmetic geometers will study it, and so on. So different people have their own take on what should be the way that you try to understand a tau function. But there is a closed formula. One of them is, and that's probably how Ramanujan came across or had these insights about the tau function. It's closely related to Euler's phi function. So phi powers of the phi function are related to the tau function.
So another question is, what is so special about the 11th power of the prime, which appears in many formulas?
I don't know. That's p to the power 11 that Ramanujan observed, that you have this inequality which comes square root of p to the power 11. I don't know.
So this one asks, so you have said multiple times that convergence was very vague when Riemann and Euler worked. Even then, why did they choose to work on these concepts if they were not very clear? And what did they think?
I mean, that's how mathematics is sort of built. I mean, even today, if you talk to a mathematics researcher, that's how mathematics and mathematical ideas develop. You have a certain kind of intuition. You might not be able to make things precise, but you have this feeling that this should be correct. This is the way which is probably things should move. But then you don't have the tools or the language to build it, and then you come up with that insight, and then the tools and the language makes it rigorous. I often like to tell this to people, especially to physicists. All the string theorists or the experimental physicists, they are trying to prove, just imagine a closed door, and they're trying to prove, after opening the door, why those things are there. They see something behind a closed door and they like to prove why those things are there. Whereas a mathematician doesn't open the door but makes a prediction of what's behind the closed door. And often the physicists realize that the mathematicians were correct. I mean, take the discovery of the Higgs boson. Even though it's a Nobel Prize in physics, 70% of it is mathematics. It was predicted by mathematicians. So a large part of abstract mathematics is intuition. After all, that's why Galileo said, right? Galileo is supposed to have made this famous quote, learn math, learn math. That's the language in which God has written the universe.
So this one asks, is there a relation between the divisor tau function and Ramanujan's tau function? So I think you have already.
Yeah, I did that. I gave you one of the identities.
Yeah.
So that's the relation. But there are so many more identities about the Ramanujan tau function where some of the other multiplicative functions show up. Okay, by the way, here is another thing that's still not unknown. sorry, that's still open about the Ramanujan tau function. So tau of n, it can never be 0. Is that true? It's believed, but there are lots of results known in that direction. Up to n very large, people know that it never becomes 0. But to prove it in general, tau of n can never be 0, nobody knows, though it's expected.
So you mean it is expected that tau of n is non-zero, or?
It's never 0. We know it's non-zero. After all, I wrote down non-zero values for that. But you can ask for some value of n. We also saw that tau of n becomes positive and negative.
Yes.
So you can ask, does it acquire the value 0 anywhere? See, if it was a continuous real valued function and it acquired positive values and real negative values, you know that it should be 0 somewhere. Right? But tau is not a real, it's not a continuous real valued function. It's an arithmetic function and you expect that it is never 0 and you have lots of evidence to support it, but you don't know that in general. You don't have abstract, complete proof that this is true, though mathematicians believe it. Yeah.
I have several more questions, but before that, Professor Geeta Venkataraman wants to ask you something. So
sure. Yeah.
she can ask.
Hi, Geeta.
Sorry, I just unmuted. Hi, Sujatha. Thank you for
Hi,
a
Geeta.
lovely talk. I'm hearing you after a few years, I think. It's because it's your talk that I decided to be ready and listen to it.
Thanks,
I
that's
wanted
very
to
kind.
ask you actually three things. One is that, I've quite a while ago for undergrads in Delhi University, I was trying to write up something on Ramanujan's life and mathematics. And it every time you look at what he did, it just strikes you as, unimaginable. The kind of
Yeah,
intuition
yeah,
that with which from the smallest to biggest things that he writes down is quite extraordinary. So
yeah.
I would like you to comment on, what do you think, how did he do this? Because
Somebody knows, Ken Ono, the mathematician who
yeah,
I like to refer to him as a great devotee of Ramanujan.
yes, yes.
So Ken Ono said that if he had a time machine and if there was one person's mind he could enter, that would be Ramanujan.
Yeah, it's,
And similarly, the Japanese mathematicians, I was trained in algebra, as you know, Geeta.
yes.
And then later in life, I moved to number theory. And when I went to Japan and worked with the mathematicians there, for them, after Germany, it was Japan which did a lot of work in modular forms. And the Japanese mathematicians, especially after the war, that generation, for them, Ramanujan is a great inspiration.
Mm.
Because apparently, Sayre, again, this was a story I learned from Ken Ono. Ken Ono's father was one of them who was heavily influenced by Ramanujan. So Sayre went to some conference in Japan, and then the Japanese mathematicians were their morale was very low after the war. And in order to cheer them up, Sayre said, I understand your difficulties, how depressing it must be, but let me tell you a story of somebody who faced even greater difficulties than you, but who did phenomenal work. And then told them about Ramanujan. And so for them, India was the land of the Buddha and Ramanujan.
That's really wonderful to hear.
Yeah.
The second question was that, the other function of Ramanujan that comes up a lot is the mock theta function.
Yeah.
I don't know much about it, but is there any connection at
Yeah,
all?
the mock theta function, there are something called mock modular forms, meaning they are not really modular forms, but they are pretending to be modular forms. So the coefficients there come up like mock theta functions. And again, it's very, of course, I'm not an expert in all this. Ken has given a lot of talks on that. You can find some of them are, I think, even accessible. So, and for me, what's again fascinating is these mock theta, these coefficients that come up in mock theta modular forms, they're related to these numbers, these monster groups, the groups, the classification of finite simple groups. You
Yeah,
have
yeah,
this huge, yeah. So these coefficients
yeah.
come up there for some reason. They come up in representation theory. And then weirdest of all, they come up in string theory and in mathematical physics.
It's almost like there's some universe constants or galactic constants, something, right? Part
Yeah.
of the fabric, maybe. Yeah. And the third thing, Sujata, is that I wanted you to share with everybody how you got into mathematics, because I think that's also quite interesting.
Well, I don't know. I mean, I always like to think that, I mean, there's an advantage to deprivation. Let me put it that way. So even though I grew up in Bangalore, I mean, we never had books like we have today, and our sole entertainment in the summer holidays. I mean, those days you didn't go on vacation. At most when my grandparents went to Tamil Nadu, they would take us for a few days. My mother's side, all the relatives were in Bangalore. So summer vacations largely meant going to the public library because they had comics there and they were free and you could read them. And then the other thing for summer, which my brother and I, my late brother and I, we used to look forward to greatly, was getting the textbooks of our seniors. And then we would finish English, he would finish English and recommend the English parts that I should read. I would finish mathematics and recommend the mathematics that I found interesting. The first few chapters of mathematics, it would almost be like, and for me, I think the greatest thing that I liked, my brother was some kind of a polymath. So he was very fond of literature, history. So he was a voracious reader, and he would tell me, like, for instance, he knew everything about the different kinds of planes that the Allies used in Second World War. So don't ask me how, but so things like that. These was the kind of knowledge he would pick up in the library, and I had to match him, which I could never. I was interested in mathematics, and for me, the greatest advantage was you had to understand it rather than just learning facts, right? And so
Yeah.
that I found, that's for me to this day, that's the most fascinating and endearing aspect of mathematics. You don't need to learn things by heart, you need to understand, and then the whole thing becomes easier.
Yes.
So I guess, and then again, that was a time when people appreciated. It didn't matter that it was mathematics. Like
Mm.
they really appreciated it if you were good in Kannada or if you were good in languages, in social studies, in everything. And because I used to get appreciated for being good in mathematics, that further spurred my interest.
Thanks, Sujata.
Yeah, welcome, Geeta.
So coming back again to the questions from the audience. One question is that you mentioned about an error term while talking about the Ramanujan tau function. So
Right.
what is the significance of this error term?
So again, there is a whole, I mean, you can do pages and pages have been written about the mathematics associated to the tau function. So for instance, what is this error term? The error term is what prevents it from being a multiplicative function on powers of primes. So you can ask, how does this error term behave as the primes increase or as the power r increases? And all those are difficult problems, and there's a lot of headway on those. People have solved that, people have understood, interpreted that error terms, related those error terms to other things that come up in mathematics. I'm not really an expert in that, but a lot is known on that error term. Let me say that. Yeah.
So another question is that why do you consider Z to be in the upper half plane particularly? What
Because
will happen?
because SL2Z, I mentioned this 2 by 2 matrices, they act only on the upper half plane. And in
Um,
fact, I mean, the modular forms I mentioned again, they are functions on the upper half plane. SL2Z acts on the upper half plane. And this action is very closely related to the other important things we study in complex analysis, namely the Riemann surface. Right? I mean, complex analysis, Riemann surface comes, you study them in topology, you study them also in as curves, complex curves, and so on. And there's a natural way to understand these Riemann surfaces to explicitly construct them by considering modular forms and the action on the upper half plane. Yeah.
so this is a question which is probably related to what Professor Venkataraman asked you and you answered. I'll still read it out. So Ramanujan was a great mathematician, but what made him realize these difficult facts and results, what others find really difficult to prove?
I don't
Without
know that. Yeah, sorry, go ahead.
without proper math education, what did he do to formulate these results? Because these results involve bizarre expressions that is difficult to guess by observing things.
Yeah, so again, I mean, that's one of the, again, you come back. See, I like to say that there is a certain mysterious component associated to mathematics, right? When you see these things suddenly fitting together, or when you see these, why should the values of Riemann zeta function show up somewhere in physics, in theoretical physics? So there is something mysterious, this element of mystery in mathematics. And there's also this strong input of intuition. And Ramanujan was blessed enough to have this very deep insights. Nobody understands. I don't know, to this day, uh, nobody understands. And a few years back, there was somebody from the BBC. They were making a series of programs called Incarnations or Legends or something like that. And they wanted to talk to me about Ramanujan. And they came and tried to, it was a radio show. And they tried to drift the conversation to an area by which I would say, oh, there's nothing mysterious about Ramanujan. We can explain how he came across all these formulas or how he did mathematics. And I kept resisting it. I said, no, I cannot. I mean, I have to be honest. Of course, I'm not an expert in Ramanujan's work, but even if you go to the experts, and I know quite a few of them, nobody has figured out how he wrote those formulas. Of course, not to say that all of his formulas were correct. There are quite a few that were not correct. But there are a phenomenal number of those which were correct, and people haven't understood how he wrote them. But again, I found it very interesting. The interviewer didn't want to accept that. He tried guiding me towards saying that, oh, he was somebody who came from the elite class in Indian caste hierarchy. So he must have had prior knowledge, etc., etc., etc. And I kept saying, no, I don't think so. And, after all, you're willing to accept there are things that you cannot explain when it comes to prodigies in your own civilization, especially musical prodigies, right? They have no problem in the West to accept Mozart as a child prodigy or somebody else as a child prodigy. But they had terrible problems accepting Ramanujan and not being able to explain his insights in a scientific, quote unquote, rational manner. And I think they were very disappointed that as a scientist and mathematician, I didn't cooperate. So finally, they didn't. They interviewed me, but then they never aired the show, because I kept resisting and I said, no, it is a mystery.
So we have Professor Ajit Iqbal Singh also with us. So
Oh, great. Yeah. Hi, Ajit.
So I am unmuting Professor Singh if she wants to.
Yeah.
Yeah.
No, I don't hear anything.
Yeah, hello, wonderful talk and greater still the interaction. Now,
hi, Ajit. So nice to see you.
Great. The people define functions for reasons of convergence, but then extensions are made. So Riemann zeta function has been extended to larger sets. So I would like to like you to throw light on that because audience is very much interested, it seems.
Sorry, I didn't quite understand.
No, people are asking over and over again, why did you take upper half plane only? So people define functions where they are given nicely by series, but then extensions are given by various properties of the functions and relations.
I answered that partly. That is because, of this connection between SL2Z acting on the upper half plane and the connection that it has to modular forms. And then when you take the upper half plane, take this action of modular forms or on SL2Z on the upper half plane, that gives you a natural way to go to construct an actual geometric object, namely Riemann.
Right.
Riemann surfaces.
Wonderful. Thank you.
So there is a participant, Omar. He wants to ask you the question himself. I'm unmuting him.
Yeah.
So Omar, please go.
Morning, ma'am. Omar here with you. And it was really nice to hear your presentation regarding Ramanujan's tau function. And I have just passed my class 12 examinations, and I'm really quite interested in Ramanujan's work. And yeah, so I won't make it long. And I just wanted to ask, ma'am, that basically the products which we were studying, which from where we started, the infinite product 1 minus q to the power of n to the power of 24, the whole power 24. It was basically Euler studied these products, right, ma'am? The very basics.
Euler converted this identity. That Euler identity is, this expression as an infinite product being equal to an infinite sum.
Yeah, exactly, ma'am. So I had a question, ma'am, that can't we generalize, ma'am, these kind of product? For example, if I want to generalize the infinite product 1 minus q to the power of n to the whole power of some natural number, and then we study the coefficients of those, expansions of the infinite products and make conjectures about those coefficients, ma'am.
No, first of all, I mean, there's no reason why if you take some arbitrary function like that, raise it to some power, you need to prove that an infinite sum can then converts to an infinite product, right? It's not obvious.
Okay, ma'am. Yeah.
So, and of course, today it's even more harder. At least when Riemann and others, they could get away probably with it, though they didn't. They had their intuition of what it should mean, that convergence, even though they couldn't phrase it precisely. I'm sure they knew whether it makes sense or doesn't make sense. Whereas today we know you cannot just escape, right? Today mathematics is rigorous enough. So when you write an infinite product equals an infinite sum, you will be asked to prove it because you know that an infinite product makes sense only if it converges. So where does it converge? And then similarly, an infinite sum, it makes sense only when you can make it precise. Is it a convergent object? What is its value? And so on.
Yeah. Thanks a lot. Thank you.
So I have several more questions. Do you still have some time with you, madam?
Sure. What's the time? I don't know.
It's 9:30 your time, I think now.
Okay, now let's go ahead. Yeah, 10 more minutes, 9:45 till 8:45, and then
okay,
it's okay, we can stop. Yeah.
So can you give some idea about the proof of Ramanujan's conjectures on the tau function?
Oh no, that's I mean, like I said, that is Fields Medal winning work. And in fact, not just that, but there's a whole series of you have analogs of these expected bounds for functions like the tau function. See, what is a Ramanujan conjecture? That's giving you a function that's giving you a bound on values of a certain function. Now in Langland's program, again, you have a series of such functions. You have many functions for which you need to give bounds on the values that it takes on prime numbers. So there are analogs which are inspired by Ramanujan's tau function. And in fact, even that proof of Ramanujan's bound, Deline's proof, he needed it for what's called the Weil conjectures, which itself, uses language of étale cohomology and so on. So it's just beyond anything that I can do justification to.
So a related question. So you mentioned in the talk that the 691, which appears in one of the formulas, inspired Deline to look into modular forms and its connection. So can you elaborate it a bit?
So it's this 691 is a very interesting prime number. So here is again, since I'm assuming that there must have been some common audience between this talk and I heard Manjil told me there were talks about connections between modular forms and elliptic curves, right? So
yes.
now for elliptic curves, people who know that you know that for elliptic curves there is an L function for an elliptic curve. So L function again, it's an infinite sum as well as an infinite product. L functions of elliptic curves have the same property like this L functions. You can express them as an infinite sum or as an infinite product. And modularity theorem, or this slogan that elliptic curves are modular, just means that if you take an elliptic curve, write down its L function, then there is a modular form whose L function is the same as the L function of the elliptic curve. And this is again, it's very, these are two different animals. Elliptic curves are completely geometric in nature, complex analytic geometric in nature. And then the way you define the L functions for elliptic curves is purely number theoretic. You count the number of points that the elliptic curves has over finite fields. So elliptic curve roughly is given by an equation with integer coefficients, say. And then you go take those integer coefficients, go modulo every prime p. So then you get an equation in the finite field Fp. Then you count the number of solutions. Because these are finite fields, you can actually count the solutions for those equations. So then you do this for every prime, and then build the L function where you use the number of solutions that this elliptic curve has over the finite fields. Then you get an infinite product, and it turns out to be also equal to an infinite sum. And that's the L function of an elliptic curve. Now, you can ask, suppose I have an elliptic curve. So that's given, it has an L function summation an to the power n to the power s. And then I have a modular form f, and the L function is fn n to the power s. So you can ask, okay, these two ans and fn's need not be congruent. Need not be equal. Okay, elliptic curves, okay, if they are over Q, you know that they are equal. That you can find a modular form where the coefficients are literally equal. But you can also ask, are there modular forms where these two are congruent modulo a prime? Right? So you have an infinite sum. You have two infinite sums. And let's assume that the coefficients are in integers, let's say. In integers, not necessarily in integers, they'll have to be in what's called the p-adic numbers. But let's assume, for simplicity, let's assume that the coefficients are in integers. And now if they are in integers, then you can say, when are the coefficients, for what frequency are the coefficients divisible, all the coefficients, when are they divisible by a given prime number? So then what happens is, then when I go modulo that p, or even if they're not divisible by p, I can look at the coefficients and look at these two infinite sums modulo the prime number. That is, divide each of those coefficients by the prime number and then look at the remainder. So then you get two infinite sums where the coefficients are now in Z mod P, say, for that prime. And it turns out that 691 was among the first primes where they discovered that there's an elliptic curve and a modular form such that these two coefficients become, they have the same reminders modulo 691. Which again is very, and this was what provided the clue for Serre, Deline, all of them to eventually believe that every elliptic curve comes from a modular form, or the L function of an elliptic curve is always the L function of a modular form. So that's the role. 691 was one of the first primes that provided that clue.
Okay. So one question is, can you give some motivation behind the definition of a modular form? Too late to ask this question, but
yeah, well, it comes from Fourier analysis. You see, I mean, any function which has those two properties that I mentioned on the complex upper half plane, which is holomorphic, which transforms in that way, and which is holomorphic as you go towards infinity, then it has to satisfy Fourier analysis. You know that it has to have that Q expansion, that Fourier expansion. And the way they were discovered, I don't know, it's complex analysis, but giving a motivation is, it's just like I said, the SL2Z, when people understood SL2Z, that it operates on the sphere, right? On the complex sphere, on P1, which you think of as a sphere. And then it comes from that. And in fact, okay, I'll have to use very technical words there. I said that people knew that SL2Z acts on the upper half plane for a very long time. And from that, you can manufacture Riemann surfaces. And then Riemann surfaces are geometric objects. And then you study vector bundles on these geometric objects. And these modular forms are nothing but sections of certain vector bundles. Okay, so they're related to differential forms. Modular forms are related to differential forms. And then people saw the connection between complex analysis, differential forms, and this action on the upper half plane. And that eventually led to the crystallization of modular forms.
So maybe you could mention some introductory textbooks on modular.
Oh yeah, there is a very nice textbook. Okay, the best one is Serre's Course in Arithmetic. It's a short book. and modular forms, again, you see, it starts with the lattices on the complex plane. And then when people were studying complex analysis, you already knew phi function, right? When you study the complex, what phi function is it called, Geeta? The P, well, here we call it pi. But the P, the script P that comes up in complex analysis, P and P prime on the, okay. So that's how you see an elliptic curve. You have an equation for an elliptic curve. Y squared is equal to f of x. Weierstrass phi function. Thanks. Yeah. Weierstrass phi function, that is again related to modular forms. And using those phi function, you can build a modular form called the Eisenstein series. And then using that, you can recover the equation of an elliptic curve. So people knew this in bits and pieces historically. And then they understood that the whole thing, the language to explain all this is modular forms. So the best book is Sayre's A Course in Arithmetic. That's a very beautiful book, which sort of the end of the book is the beginning of modular forms. So you read the whole transition of simple number theory to ending up in modular forms. So that's one of the recommendations. And today you have other books, but they are slightly higher level. There are also some books by Ramurthy, which are very accessible. You might even find them on his homepage. But Course in Arithmetic is a good place to start.
So I still have many questions, but one final question,
Yeah.
probably you can take. So this was asked by many people. So is your area of work also related to Ramanujan's mathematics? If yes, how?
Some of it, yes, because like I said, these L functions of modular forms and L functions of elliptic curves. There's also one part which I've never spoken about, which is everything that I spoke about was number theory or analysis, complex analysis. But there's also algebra. Because I always believe that just like mathematics makes science rigorous, algebra makes mathematics rigorous. So I work in that area where some of these number theoretic phenomena has connections with algebra. Especially, this, elliptic curves are modular. How do you explain that? Or there are other properties of these coefficients, this modular forms coefficients, congruence properties, and so on, which people knew for a long time. And again, it's these two totally different things which somehow are linked. And you can see why they are linked by going to some higher order stuff. These are two aspects, two avatars of some common ancestor, and that's why they are linked. So that's the kind of area I work in. Yeah.
So thank you so much for answering so many questions and for the very nice talk.
Yeah, thank you.
Thank you so much for your time.
Right.
I'm now closing the live stream.